Question 1. Benchmark analysis indicates that a regional industrial consortium is seeking guidance on transitioning its energy portfolio towards greater sustainability. The consortium operates under U.S. federal and state environmental regulations and is concerned with energy security, cost-effectiveness, and minimizing its environmental footprint. Which of the following approaches best aligns with the principles of environmental science and regulatory compliance for this consortium? Option A. Prioritize the continued use of the most cost-effective fossil fuels, with minimal investment in pollution control technologies, citing immediate economic benefits and established infrastructure. Option B. Focus solely on implementing aggressive energy conservation measures across all operations, assuming this will sufficiently address the consortium's energy needs and environmental concerns. Option C. Conduct a comprehensive assessment of renewable energy potential, energy efficiency opportunities, and the life cycle environmental impacts of continued fossil fuel reliance, while factoring in current and projected energy policies. Option D. Immediately cease all fossil fuel consumption and invest exclusively in the most readily available renewable energy technologies, regardless of their current cost or infrastructure compatibility. Correct answer is C. Conduct a comprehensive assessment of renewable energy potential, energy efficiency opportunities, and the life cycle environmental impacts of continued fossil fuel reliance, while factoring in current and projected energy policies. Explanation. Scenario analysis. This scenario is professionally challenging because it requires balancing competing stakeholder interests regarding energy resource development and utilization. Environmental scientists must navigate the complex interplay between economic development, energy security, public health, and ecological preservation, all within the confines of specific regulatory frameworks. The pressure to adopt readily available, cost-effective solutions, like fossil fuels, often clashes with the long-term sustainability goals mandated by environmental regulations and the growing demand for renewable energy. Accurate assessment of environmental impacts, life cycle analyses, and adherence to energy policy directives are paramount. Correct approach analysis. The correct approach prioritizes a comprehensive, data-driven evaluation of all energy options, considering their environmental, social, and economic implications. This aligns with the core principles of environmental science and the regulatory mandate to protect environmental quality and public health. By thoroughly assessing renewable energy potential, energy efficiency measures, and the life cycle impacts of fossil fuels, while also considering relevant energy policies, the scientist provides a robust foundation for informed decision-making. This approach upholds the ethical responsibility to advocate for sustainable practices and comply with regulations like the Clean Air Act and the Energy Policy Act, which promote cleaner energy sources and efficiency. Incorrect approach is analysis. An approach solely focused on the immediate cost-effectiveness of fossil fuels, without a thorough environmental impact assessment or consideration of renewable alternatives, fails to meet regulatory requirements for environmental protection and ignores the long-term sustainability goals embedded in energy policy. This represents a failure to adhere to the precautionary principle and a disregard for the cumulative environmental burden. An approach that exclusively champions renewable energy without a realistic assessment of its current feasibility, infrastructure requirements, or potential localized environmental impacts, e.g., land use for solar farms, visual impact of wind turbines, may be impractical and fail to address immediate energy needs effectively. While aspirational, it lacks the balanced, evidence-based approach required by environmental regulations. An approach that prioritizes energy conservation measures without exploring the potential for cleaner energy generation or efficiency improvements in existing infrastructure overlooks a significant component of a holistic energy strategy. While conservation is vital, it is only one piece of the puzzle and may not fully address the need for reliable and sustainable energy supply. Professional reasoning. Professionals should adopt a systematic, multifaceted approach. This involves 1. Understanding the specific regulatory landscape, e.g., U.S. EPA regulations, state-level energy policies. 2. Conducting thorough environmental impact assessments for all proposed energy sources. 3. Performing life cycle analyses to understand the full environmental footprint. 4. Engaging with stakeholders to understand their concerns and priorities. 5. Evaluating the technical and economic feasibility of various solutions, including renewable energy and energy efficiency. 6. Recommending solutions that demonstrably minimize environmental harm, promote sustainability, and comply with all applicable laws and policies. Question 2. System analysis indicates that a certified environmental scientist is conducting an environmental impact assessment for a proposed commercial development adjacent to a wetland. Preliminary field observations suggest the presence of a rare amphibian species, potentially warranting endangered status, within the wetland. The developer, eager for a swift project approval, has requested a streamlined assessment that minimizes costly mitigation strategies. The CES is aware that a comprehensive ecological survey and detailed analysis of the amphibian's habitat requirements and population dynamics will be time-consuming and potentially lead to significant mitigation demands. What is the most ethically and professionally responsible course of action for the certified environmental scientist? Option A. Recommend generic mitigation measures for wetlands without specific investigation into the amphibian species, assuming that standard practices will suffice to address any potential issues. Option B. Rely solely on the developer's provided information and preliminary site observations, without conducting independent, in-depth ecological surveys to expedite the assessment. Option C. Conduct a thorough, science-based environmental impact assessment, including detailed field surveys and habitat analysis, to accurately determine the amphibian status and potential impacts, and recommend appropriate, legally compliant mitigation measures, even if it delays the project and increases costs. Option D. Proceed with a limited assessment focusing only on readily observable impacts, downplaying the potential significance of the rare amphibian to facilitate a quicker approval process for the developer. The correct answer is C. Conduct a thorough, science-based environmental impact assessment, including detailed field surveys and habitat analysis, to accurately determine the amphibian's status and potential impacts, and recommend appropriate, legally compliant mitigation measures, even if it delays the project and increases costs. Explanation. Scenario analysis. This scenario presents a professional challenge due to the conflict between immediate economic pressures and long-term ecological integrity. The Certified Environmental Scientist, CES, is tasked with assessing the environmental impact of a proposed development, which involves a sensitive wetland ecosystem. The wetland is a critical habitat for several species, including a potentially endangered amphibian. The developer is pushing for a swift approval process, implying a desire to minimize costly mitigation measures. The CES must balance the scientific imperative to protect biodiversity and ecosystem function with the client's commercial interests and the need for timely project progression. This requires a deep understanding of ecological principles, regulatory requirements, and ethical obligations. Correct approach analysis. The correct approach involves conducting a thorough, science-based environmental impact assessment (IA) that rigorously evaluates the potential effects on the wetland ecosystem and its inhabitants, particularly the amphibian species. This includes detailed field surveys, habitat assessments, and the application of established ecological methodologies to determine population status and potential threats. The CES must then clearly articulate the findings, including any risks to biodiversity and ecosystem services, and recommend appropriate mitigation and avoidance strategies that are scientifically sound and legally defensible under the relevant U.S. environmental regulations, e.g., Endangered Species Act, Clean Water Act, NEPA. This approach upholds the CES's professional responsibility to provide objective, evidence-based advice, ensuring compliance with environmental laws and promoting sustainable development. It prioritizes the protection of natural resources and adheres to the ethical principles of environmental stewardship. Incorrect approach is analysis. One incorrect approach would be to downplay the significance of the amphibian species or the wetland's ecological functions to expedite the approval process and satisfy the developer's timeline. This would constitute a failure to adhere to the scientific rigor expected of a CES and could violate regulatory requirements such as the Endangered Species Act, which mandates protection for listed or potentially listed species. Ethically, it represents a dereliction of duty to protect environmental resources. Another incorrect approach would be to recommend overly simplistic or ineffective mitigation measures that do not adequately address the identified ecological risks. For instance, proposing minor habitat alterations without a clear understanding of the amphibian's life cycle or the wetland's hydrological regime would be scientifically unsound and likely insufficient to meet regulatory standards. This approach demonstrates a lack of professional competence and could lead to irreversible environmental damage, violating professional codes of conduct and environmental laws. A third incorrect approach would be to solely rely on the developer's preliminary data or assumptions without independent verification. This would compromise the objectivity of the EIA and could lead to an incomplete or inaccurate assessment of environmental impacts. It would fail to meet the due diligence requirements of professional practice and could expose the CES to liability if environmental harm occurs due to an inadequate assessment. Professional reasoning. Professionals should approach such situations by first clearly identifying all relevant regulatory frameworks and scientific literature pertaining to the specific ecosystem and species in question. They must then develop a comprehensive work plan that prioritizes data collection and analysis to address potential impacts. Communication with the client should be transparent, outlining the scope of work, potential findings, and the importance of adhering to scientific and regulatory standards. When faced with pressure to compromise scientific integrity or regulatory compliance, professionals must firmly advocate for the scientifically defensible and legally required course of action, documenting all decisions and recommendations. If client pressure leads to a situation where professional ethics or legal obligations cannot be met, the CES has a responsibility to consider withdrawing from the project. Question 3. Research into optimizing the management of legacy contamination at a former industrial facility has identified several potential hazardous substances. Which approach best integrates the principles of risk assessment and management to guide the selection of remediation strategies, considering both effectiveness and resource allocation? Option A. Prioritize remediation efforts based solely on the historical presence of the most toxic substances identified during initial site investigations, without a detailed assessment of current exposure pathways or potential for future exposure. Option B. Focus exclusively on identifying and characterizing the physical and chemical properties of all potential contaminants, and then communicate these findings to regulatory bodies without developing specific risk management strategies or considering exposure scenarios. Option C. Implement a single, high-cost, technologically advanced remediation strategy for all identified contaminants, assuming this will provide the most comprehensive risk reduction, regardless of the specific exposure levels or the cost-effectiveness of alternative approaches. Option D. Conduct a comprehensive site-wide risk assessment, including detailed hazard identification, exposure assessment, dose-response assessment, and risk characterization, with a specific focus on quantifying uncertainties. Subsequently, develop and evaluate a range of risk management options, prioritizing those that offer the most significant risk reduction per unit of investment, and engage in transparent risk communication with regulatory agencies and affected communities. The correct answer is D. Conduct a comprehensive site-wide risk assessment, including detailed hazard identification, exposure assessment, dose-response assessment, and risk characterization, with a specific focus on quantifying uncertainties. Subsequently, develop and evaluate a range of risk management options, prioritizing those that offer the most significant risk reduction per unit of investment, and engage in transparent risk communication with regulatory agencies and affected communities. Explanation. This scenario presents a common challenge in environmental science, optimizing risk management strategies for a complex industrial site with multiple potential hazards and exposure pathways. The professional challenge lies in balancing the need for effective risk reduction with resource constraints, regulatory compliance, and the inherent uncertainties in environmental data and modeling. Careful judgment is required to prioritize actions that yield the greatest risk reduction for the investment, while ensuring all regulatory requirements are met and stakeholder concerns are addressed. The correct approach represents best professional practice because it systematically integrates all phases of the risk assessment process to inform a targeted and efficient risk management strategy. It begins with a thorough hazard identification and exposure assessment to understand the scope of potential risks. The dose-response assessment provides the scientific basis for quantifying these risks, and risk characterization synthesizes this information to estimate the likelihood and magnitude of adverse effects. Crucially, this approach emphasizes uncertainty analysis to acknowledge and manage the limitations of the assessment, which is a fundamental ethical and regulatory requirement. Finally, it links these findings directly to the development of risk management strategies, prioritizing those that are most effective and cost-efficient, and includes robust risk communication to ensure transparency and informed decision-making by stakeholders. This holistic and iterative process aligns with the principles of sound environmental management and regulatory compliance, ensuring that resources are allocated effectively to protect human health and the environment. An incorrect approach that focuses solely on hazard identification without a comprehensive exposure assessment would be professionally unacceptable. This failure would lead to a misallocation of resources, potentially addressing hazards that pose little actual risk due to negligible exposure, while overlooking significant risks from other sources. Ethically, this is a failure to adequately protect human health and the environment. Another incorrect approach that prioritizes a single, high-cost risk management strategy without a thorough risk characterization or consideration of uncertainty would also be professionally flawed. This could result in an unnecessary expenditure of resources on a strategy that offers marginal risk reduction, or worse, a strategy that is ineffective against the actual dominant risks. This violates the principle of efficient resource allocation and potentially fails to meet regulatory objectives for risk reduction. A third incorrect approach that neglects risk communication and stakeholder engagement would be ethically and regulatorily deficient. Environmental decisions have broad societal implications, and failing to communicate findings and involve stakeholders in the decision-making process erodes public trust and can lead to significant implementation challenges. This is a failure to uphold transparency and accountability. The professional decision-making process for similar situations should involve a structured, iterative approach to risk assessment and management. This includes clearly defining the scope and objectives of the assessment, systematically identifying all potential hazards and exposure pathways, conducting robust exposure and dose response assessments, characterizing risks, including quantifying uncertainty, developing and evaluating a range of risk management options based on effectiveness, cost, and feasibility, selecting and implementing the most appropriate strategies, and establishing ongoing monitoring and communication protocols. This process ensures that decisions are scientifically sound, ethically defensible, and compliant with all applicable regulations. Question 4. Stakeholder feedback indicates a need to assess potential organic contamination in soil at a former industrial facility. The site is subject to U.S. EPA regulations for hazardous waste site cleanup. Given the historical use of the site, a range of chlorinated solvents and petroleum hydrocarbons are suspected. The project has a defined budget and timeline for initial site characterization. Which of the following analytical approaches best balances regulatory compliance, cost-effectiveness, and the need for reliable data? Option A. Select the least expensive laboratory analytical method available for general organic compound analysis, regardless of its specificity or detection limits for known contaminants. Option B. Conduct a broad, non-targeted gas chromatography mass spectrometry, GCMS, scan for all detectable organic compounds in the soil to identify any unexpected contaminants. Option C. Rely exclusively on portable photoionization detectors, PID, for field screening of total volatile organic compounds, VOC, to quickly delineate potential areas of concern. Option D. Prioritize laboratory analysis for a defined list of regulated organic compounds, e.g., VOC, SVOC, PA, known to be associated with the suspected historical industrial activities and relevant to U.S. EPA cleanup standards, using methods with appropriate detection limits. The correct answer is D. Prioritize laboratory analysis for a defined list of regulated organic compounds, e.g., VOC, SVOC, PA, known to be associated with the suspected historical industrial activities and relevant to U.S. EPA cleanup standards, using methods with appropriate detection limits. Explanation. Scenario analysis. This scenario presents a common challenge for environmental scientists, balancing the need for accurate chemical analysis with the practical constraints of project timelines and budgets, while also ensuring compliance with regulatory standards. The complexity arises from the potential for various organic compounds to be present in the soil, each with different chemical properties, environmental fates, and analytical detection limits. The scientist must make a critical decision about the analytical approach that will yield the most reliable and defensible data for regulatory purposes, without incurring unnecessary costs or delays. Correct approach analysis. The correct approach involves prioritizing the analysis of specific, regulated organic pollutants known to be of concern in the region, based on historical data, site use, and regulatory lists. This aligns with the principles of targeted chemical analysis, which is a cornerstone of environmental regulatory compliance. By focusing on compounds with established environmental quality standards, e.g., under U.S. EPA regulations for contaminated sites, the scientist ensures that the data collected will directly address the regulatory objectives. This approach is cost-effective, time-efficient, and provides data that is directly interpretable within the legal and scientific framework governing environmental protection. It demonstrates a commitment to regulatory adherence and responsible resource allocation. Incorrect approaches analysis. One incorrect approach would be to conduct a broad, non-targeted screening analysis for all detectable organic compounds without prior prioritization. This is often prohibitively expensive and time-consuming, and the resulting data may be overwhelming and difficult to interpret in the context of specific regulatory requirements. It fails to demonstrate due diligence in focusing on known or suspected contaminants of concern, and may lead to the generation of irrelevant data, wasting resources, and potentially delaying remediation efforts. Ethically, it represents a failure to act in a cost-effective and efficient manner. Another incorrect approach would be to rely solely on field screening methods without laboratory confirmation for regulated analytes. While field screening can be useful for initial site characterization, it often lacks the precision and specificity required for regulatory compliance. Many field methods have higher detection limits or are prone to interferences, leading to potentially inaccurate assessments of contamination levels. This could result in either over-remediation or under-remediation, both of which have significant environmental and financial consequences, and violate the ethical obligation to provide accurate and reliable data to regulatory bodies. A third incorrect approach would be to select analytical methods based purely on the lowest cost, without considering their suitability for detecting the target analytes at the required regulatory limits. This can lead to the use of inappropriate methods that cannot accurately quantify the contaminants of concern, rendering the data unusable for regulatory decision-making. This is a direct violation of regulatory requirements and an ethical breach, as it compromises the integrity of the environmental assessment. Professional reasoning. Environmental scientists must employ a systematic decision-making process when selecting analytical approaches. This involves 1. Understanding the regulatory context and identifying all relevant federal, state, and local regulations governing the site and potential contaminants. 2. Reviewing historical site data and conducting a preliminary site assessment to identify potential sources and types of contamination. 3. Consulting regulatory guidance documents and lists of priority pollutants. 4. Evaluating the capabilities and limitations of various analytical techniques, including their detection limits, specificity, and cost. 5. Prioritizing analytes based on regulatory concern, toxicity, mobility, and persistence. 6. Selecting analytical methods that are appropriate for the identified analytes and will meet regulatory data quality objectives. 7. Documenting the rationale for all analytical decisions. Question 5. System analysis indicates that a public drinking water system's surface water intake is monitored regularly for various parameters. Recent sampling data from the intake point shows occasional exceedances of a specific inorganic contaminant above the maximum contaminant level, MCL, established by the U.S. EPA. Additionally, upstream surface water monitoring stations have detected elevated levels of certain organic compounds, and nearby groundwater monitoring wells have shown trace amounts of nitrates. Considering the principles of risk assessment for drinking water sources, which approach best addresses the potential risks to public health? Option A. Conduct a comprehensive risk assessment that integrates data from all monitoring points, intake, upstream, groundwater, evaluates the frequency and magnitude of all parameter exceedances against relevant U.S. EPA drinking water standards and guidance, and considers potential contamination pathways and treatment effectiveness. Option B. Base the risk assessment primarily on the most recent sampling event at the intake, as this reflects the current condition of the water source. Option C. Prioritize the organic compound detections from upstream stations, assuming these are the primary drivers of potential future contamination at the intake. Option D. Focus solely on the inorganic contaminant exceedances at the intake point, as this is the most direct indicator of potential risk to the treated water. The correct answer is A. Conduct a comprehensive risk assessment that integrates data from all monitoring points, intake, upstream, groundwater, evaluates the frequency and magnitude of all parameter exceedances against relevant U.S. EPA drinking water standards and guidance, and considers potential contamination pathways and treatment effectiveness. Explanation. Scenario analysis. This scenario presents a common challenge in environmental consulting, interpreting complex water quality data to inform a risk assessment for a public drinking water source. The challenge lies in synthesizing information from multiple monitoring points, considering various parameters, and understanding the implications of potential exceedances against established drinking water standards. Professionals must exercise sound judgment to differentiate between transient fluctuations and significant contamination events that pose a public health risk. The integration of sampling techniques, analytical methods, and data interpretation is crucial for a defensible risk assessment. Correct approach analysis. The correct approach involves a systematic evaluation of all collected data against relevant U.S. EPA drinking water standards and guidance documents. This includes assessing the frequency and magnitude of parameter exceedances, considering the specific sampling locations, surface water intake, upstream sources, and understanding the analytical methods used to ensure data reliability. A robust risk assessment will then consider the potential pathways of contamination, the vulnerability of the population served, and the effectiveness of existing treatment processes. This comprehensive approach aligns with the Safe Drinking Water Act, (ESTWA), and EPA guidance on risk assessment, ensuring that public health is protected by identifying and mitigating potential threats to drinking water quality. It represents best professional practice by prioritizing a thorough, evidence-based evaluation of potential risks. Incorrect approaches analysis, focusing solely on a single parameter, even if it exceeds a standard, is an incomplete risk assessment. This fails to consider the synergistic effects of multiple contaminants or the potential for other parameters to indicate an underlying issue. It is a regulatory failure because it does not fulfill the comprehensive monitoring and assessment requirements of the ESTWA. Ignoring data from upstream monitoring points or groundwater sources is a significant oversight. Contamination can originate from various sources and travel through different pathways. A complete risk assessment must consider all potential inputs to the drinking water source, as mandated by the ESTWA focus on source water protection. This approach is ethically problematic as it potentially underestimates risks to the public. Relying only on the most recent sampling event without considering historical trends is also a flawed approach. Water quality can fluctuate seasonally or due to specific events. Understanding historical data provides context and helps identify emerging issues or patterns that might not be apparent from a single snapshot in time. This failure to consider temporal trends can lead to an inaccurate assessment of long-term risk, violating the spirit of the ESTWA mandate for ongoing protection. Professional reasoning. Environmental scientists must adopt a holistic and systematic approach to risk assessment. This involves 1. Clearly defining the scope and objectives of the assessment. 2. Gathering all relevant data, including historical records and data from all monitoring points. 3. Understanding the limitations and reliability of the data based on sampling techniques and analytical methods. 4. Comparing data against applicable regulatory standards, e.g., U.S. EPA MCLs for drinking water. 5. Evaluating potential exposure pathways and population vulnerability. And 6. Communicating findings clearly and concisely to stakeholders, including recommendations for mitigation and further monitoring. This structured process ensures that decisions are data-driven, scientifically sound, and compliant with regulatory requirements, ultimately safeguarding public health and the environment. Question 6. Which approach would be most appropriate for a certified environmental scientist tasked with evaluating the potential air quality impacts of a proposed new manufacturing facility that will emit volatile organic compounds, VOC, and particulate matter, considering the prevailing local weather patterns and the proximity of residential areas? Option A. Conduct a detailed dispersion modeling analysis using site-specific meteorological data and emission estimates, comparing predicted ambient concentrations to relevant U.S. EPA National Ambient Air Quality Standards, NOx, and considering the potential for secondary pollutant formation. Option B. Focus primarily on the total annual tonnage of VOCs and particulate matter emitted, assuming that any emissions above a certain threshold will automatically require significant pollution control measures. Option C. Utilize general air quality data from the nearest major metropolitan area to estimate the potential impact, as the proposed facility is located in a rural region. Option D. Recommend the installation of the most advanced and expensive pollution control technology available, regardless of the actual predicted impact, to ensure maximum emission reduction. The correct answer is A. Conduct a detailed dispersion modeling analysis using site-specific meteorological data and emission estimates, comparing predicted ambient concentrations to relevant U.S. EPA National Ambient Air Quality Standards, NOx, and considering the potential for secondary pollutant formation. Explanation: Scenario analysis. This scenario presents a common challenge for environmental scientists, assessing the potential impact of a new industrial facility on local air quality and human health. The challenge lies in integrating complex atmospheric science principles with regulatory requirements to make a sound recommendation. Professionals must consider not only the direct emissions, but also how atmospheric conditions will influence their dispersion and potential for harm. The decision-making process is further complicated by the need to balance industrial development with public health and environmental protection, often under time constraints and with incomplete data. Correct approach analysis. The correct approach involves a comprehensive assessment that considers the specific atmospheric conditions relevant to the proposed site and the nature of the emissions. This includes analyzing prevailing wind patterns, atmospheric stability, and local topography to predict how pollutants will disperse. It also requires understanding the chemical transformations that may occur in the atmosphere and their potential to form secondary pollutants. Furthermore, it necessitates comparing predicted ambient concentrations against established air quality standards and guidelines, such as those set by the U.S. Environmental Protection Agency, EPA, under the Clean Air Act. This approach is best professional practice because it is data-driven, scientifically rigorous, and directly addresses the regulatory mandate to protect public health and the environment from harmful air pollution. It demonstrates a commitment to due diligence and responsible environmental stewardship. Incorrect approach is analysis. One incorrect approach would be to solely focus on the quantity of emissions without considering atmospheric transport and dispersion. This fails to acknowledge that even high emission rates may pose minimal risk if pollutants are rapidly dispersed and diluted by favorable meteorological conditions. Ethically, this approach is flawed as it could lead to an underestimation of risk and inadequate protective measures. Legally, it would likely violate the spirit and letter of air quality regulations that require consideration of actual ambient concentrations. Another incorrect approach would be to rely solely on generic air quality data from a distant location. This ignores the unique microclimate and topographical features of the proposed facility site, which can significantly influence pollutant dispersion. Such an approach is scientifically unsound and could lead to inaccurate risk assessments. It represents a failure in professional responsibility to conduct site-specific evaluations as mandated by regulatory frameworks. A third incorrect approach would be to prioritize the economic feasibility of pollution control technologies over a thorough environmental impact assessment. While cost is a factor, it should not override the primary objective of protecting public health and the environment. This approach is ethically questionable, as it places financial interests above environmental and health concerns, and it is legally problematic as it may not meet the stringent requirements of environmental regulations. Professional reasoning. Professionals facing such a scenario should adopt a systematic, science-based approach. This involves 1. Clearly defining the scope of the assessment, including the pollutants of concern and the geographical area to be studied. 2. Gathering relevant meteorological data, emission inventories, and dispersion modeling parameters. 3. Conducting a thorough dispersion modeling analysis to predict ambient concentrations. 4. Comparing predicted concentrations to applicable air quality standards and health-based guidelines. 5. Evaluating potential cumulative impacts and synergistic effects. And 6. Developing a clear, concise report with actionable recommendations for mitigation and monitoring, all while adhering to the principles of scientific integrity and regulatory compliance. Question 7. The review process indicates that a proposed development site is located in a region with a history of seismic activity and is situated above a known fault line. The initial environmental impact assessment, IA, primarily focused on surface water runoff and soil contamination, with only a cursory mention of geological hazards. As the certified environmental scientist responsible for the project's environmental integrity, what is the most appropriate approach to address the potential geological risks? Option A. Prioritize the project's economic viability by implementing minimal, low-cost engineering solutions for potential ground instability, as the probability of a major seismic event is considered low. Option B. Rely on the existing geological maps and regional seismic data, assuming that the project's footprint does not directly intersect the identified fault line, and proceed with the current mitigation plans for surface water and soil. Option C. Focus solely on the immediate environmental impacts of construction, such as dust and noise pollution, and defer any in-depth geological hazard assessment to the operational phase of the project. Option D. Conduct a detailed geological hazard assessment, including subsurface investigations, seismic risk analysis, and modeling of potential ground deformation, to inform mitigation strategies and project design. The correct answer is D. Conduct a detailed geological hazard assessment, including subsurface investigations, seismic risk analysis, and modeling of potential ground deformation, to inform mitigation strategies and project design. Explanation. The review process indicates a potential oversight in the initial environmental impact assessment for a proposed infrastructure project. The challenge lies in accurately assessing the long-term implications of geological hazards on project sustainability and public safety, particularly concerning the interaction between the project's footprint and underlying geological formations. This requires a deep understanding of Earth structure, plate tectonics, and the potential for seismic activity or ground instability. A professionally sound approach involves a comprehensive geological hazard assessment that goes beyond surface-level observations. This includes detailed subsurface investigations, analysis of historical seismic data, and modeling of potential ground deformation or liquefaction. Such an approach aligns with the principles of due diligence and responsible environmental stewardship mandated by regulatory frameworks that require proactive identification and mitigation of significant environmental risks. It ensures that the project design incorporates appropriate safeguards, minimizing potential harm to the environment and human populations, and adhering to the precautionary principle inherent in environmental science. An approach that relies solely on existing geological maps without site-specific investigation is professionally deficient. This fails to account for localized variations in geological conditions and potential undocumented hazards, violating the regulatory requirement for a thorough and accurate assessment. Similarly, an approach that prioritizes cost-effectiveness by downplaying potential geological risks, even if not explicitly prohibited by current regulations, represents an ethical failure. It demonstrates a disregard for the potential for catastrophic events and the long-term environmental and societal consequences, undermining the core ethical obligations of a certified environmental scientist to protect public health and the environment. Focusing only on immediate construction impacts without considering the long-term geological stability of the site also represents a failure to meet the comprehensive scope of environmental impact assessments. Professionals should adopt a risk-based decision-making framework. This involves systematically identifying potential geological hazards, evaluating their likelihood and potential impact, and developing robust mitigation strategies. This process should be iterative, incorporating new information as it becomes available and prioritizing the most significant risks. Consulting with specialized geologists and seismologists is crucial when dealing with complex geological settings. Question 8. The analysis reveals that soil samples collected from a former industrial site exhibit elevated concentrations of volatile organic compounds, VOC, and semi-volatile organic compounds, SVOC, based on both portable X-ray fluorescence, PXRF, screening and laboratory gas chromatography mass spectrometry, GCMS analysis. However, the PXRF screening indicated a broader spatial distribution of potential contamination than the GCMS results, particularly for SVOC. Sediment samples from an adjacent creek show trace levels of metals, with laboratory inductively coupled plasma mass spectrometry (IPMS) confirming the presence of lead and arsenic at concentrations slightly above background, but below state-specific sediment quality guidelines. Considering these findings and the need to develop a remediation plan, which approach best aligns with U.S. environmental regulatory principles for soil and sediment assessment and remediation. Option A. Prioritize remediation of VOCs and SVOC in soil based on the broader spatial distribution indicated by PXRF, while considering the metals in sediment as not requiring immediate action due to being below regulatory guidelines. Option B. Implement a cost-effective remediation strategy for the metals in sediment, as they are present in a sensitive aquatic environment, and defer detailed soil remediation planning until further site investigation clarifies the PXRF/GCMS discrepancies. Option C. Focus remediation efforts solely on the VOCs and SVOC identified by GCMS in soil, as laboratory results are generally considered more definitive than field screening, and disregard the PXRF findings for SVOC due to the discrepancy. Option D. Conduct a detailed risk assessment for both soil and sediment, integrating all analytical data, PXRF and laboratory, to determine the extent and nature of contamination, and then select a remediation strategy that addresses all identified risks in a technically sound and regulatory compliant manner. The correct answer is A. Prioritize remediation of VOCs and SVOC in soil based on the broader spatial distribution indicated by PXRF, while considering the metals in sediment as not requiring immediate action due to being below regulatory guidelines. Explanation: this scenario presents a common challenge for certified environmental scientists, interpreting complex soil and sediment data to inform remediation decisions. The challenge lies in the potential for conflicting results from different analytical methods and the need to select the most appropriate remediation strategy based on regulatory compliance and site-specific conditions. Careful judgment is required to balance cost-effectiveness, technical feasibility, and environmental protection. The correct approach represents best professional practice because it prioritizes a comprehensive understanding of contaminant distribution and fate, aligning with the U.S. EPA's regulatory framework for soil and sediment assessment and remediation. This involves using multiple lines of evidence, including both field screening and laboratory analysis, to characterize the extent and nature of contamination. The chosen remediation strategy is then directly informed by this robust characterization, ensuring compliance with relevant regulations such as the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, or the Resource Conservation and Recovery Act, RCRA, depending on the site's history and regulatory status. Ethical considerations demand that the chosen strategy is protective of human health and the environment, which is best achieved through thorough and accurate data interpretation. An incorrect approach that relies solely on field screening data without laboratory confirmation would be professionally unacceptable. This is because field screening methods, while useful for rapid assessment, often have limitations in sensitivity, specificity, and accuracy compared to laboratory analyses. Such an approach could lead to either over-remediation, unnecessary costs and resource expenditure, or under-remediation, failure to adequately address contamination, both of which violate the ethical duty to protect public health and the environment, and could lead to non-compliance with regulatory standards. Another incorrect approach that focuses on a single contaminant without considering potential synergistic effects or the presence of other co-contaminants would also be professionally flawed. Environmental systems are complex, and contaminants can interact in ways that affect their mobility, toxicity, and persistence. Ignoring these interactions can lead to an incomplete risk assessment and an ineffective remediation strategy, failing to meet regulatory requirements for a holistic site assessment and potentially posing long-term environmental risks. A third incorrect approach that selects a remediation strategy based solely on cost without a thorough technical and regulatory evaluation would be ethically and professionally unsound. While cost is a factor, it cannot supersede the primary objectives of environmental protection and regulatory compliance. A technically inappropriate or non-compliant remediation method, even if inexpensive, would not achieve the desired environmental outcomes and could result in significant long-term liabilities and regulatory penalties. The professional reasoning process for similar situations should involve a systematic approach. 1. Thoroughly review all available data, including field screening and laboratory results. 2. Identify any discrepancies or uncertainties in the data and plan for further investigation or clarification if necessary. 3. Evaluate the data in the context of relevant U.S. federal and state environmental regulations, e.g., CERCLA, ARCRA, Clean Water Act for sediment. 4. Consider the physical and chemical properties of the identified contaminants and their potential fate and transport in the environment. 5. Develop and evaluate multiple potential remediation strategies, considering their technical feasibility, cost-effectiveness, regulatory compliance, and long-term effectiveness. 6. Select the most appropriate remediation strategy based on a comprehensive risk assessment and regulatory requirements, documenting the rationale for the decision. Question 9. Compliance review shows that a manufacturing facility has been generating a significant volume of chemical byproducts. Management is pressuring the environmental department to find the most cost-effective disposal method immediately, suggesting that a thorough characterization of all waste streams and the development of a comprehensive waste minimization plan can be deferred to a later date to save on upfront expenses. As the certified environmental scientist responsible for waste management, what is the most appropriate course of action? Option A. Focus solely on meeting the minimum regulatory requirements for waste disposal, utilizing the most readily available disposal service without conducting further characterization or exploring reduction strategies. Option B. Immediately initiate a detailed waste characterization process for all byproduct streams and develop a phased waste minimization strategy, presenting the findings and proposed plan to management with a clear explanation of regulatory requirements and long-term benefits. Option C. Proceed with the cheapest available disposal method for the byproducts, assuming they are non-hazardous, and inform management that a formal waste characterization and minimization plan will be developed once immediate disposal costs are managed. Option D. Agree to defer the waste characterization and minimization plan, prioritizing immediate cost savings, and proceed with disposal based on management's initial assumptions about the waste's non-hazardous nature. Correct answer is B. Immediately initiate a detailed waste characterization process for all byproduct streams and develop a phased waste minimization strategy, presenting the findings and proposed plan to management with a clear explanation of regulatory requirements and long-term benefits. Explanation. Scenario analysis. This scenario presents a professional challenge due to conflicting pressures. The Certified Environmental Scientist, CES, is tasked with ensuring compliance with waste management regulations, while also facing pressure from management to minimize immediate operational costs. This creates an ethical dilemma where the CES must balance regulatory obligations with business interests, potentially leading to shortcuts that could have long-term environmental and legal consequences. The CES's professional integrity and adherence to the Certified Environmental Scientist Code of Ethics are paramount. Correct approach analysis. The correct approach involves prioritizing thorough waste characterization and the implementation of a comprehensive waste minimization plan, even if it incurs higher upfront costs. This aligns with the principles of responsible waste management, which emphasize the waste hierarchy: reduce, reuse, recycle, recover, dispose. Specifically, it adheres to the spirit and letter of regulations that mandate proper handling and disposal of waste, particularly hazardous waste, and encourage pollution prevention. By conducting detailed characterization, the CES ensures accurate classification, which dictates appropriate disposal methods and prevents improper disposal that could lead to environmental contamination and significant penalties. Developing and implementing a waste minimization strategy demonstrates proactive environmental stewardship and long-term cost-effectiveness through reduced waste volumes and potential resource recovery, reflecting best professional practice. Incorrect approaches analysis. One incorrect approach involves relying on a superficial waste assessment and proceeding with disposal based on assumptions to reduce immediate costs. This fails to meet regulatory requirements for accurate waste characterization, which is a foundational element of proper waste management. It risks misclassifying waste, leading to improper disposal, potential environmental harm, and severe legal repercussions, including fines and criminal charges. Ethically, It violates the CES's duty to protect public health and the environment. Another incorrect approach is to defer the implementation of waste minimization strategies, citing budget constraints, and opting for the cheapest disposal method available without proper characterization. This directly contravenes the regulatory emphasis on waste reduction and pollution prevention. It prioritizes short-term financial gains over long-term environmental responsibility and regulatory compliance. Such an approach can lead to the accumulation of waste, increased disposal costs over time, and potential liability for environmental damage. A third incorrect approach is to solely focus on meeting the minimum regulatory requirements for disposal without exploring any waste reduction or recycling opportunities. While technically compliant with disposal mandates, this approach misses the broader ethical and professional responsibility to minimize environmental impact. Regulations often encourage or mandate waste reduction efforts, and a CES is expected to go beyond mere compliance to promote sustainable practices. Failing to do so represents a missed opportunity for environmental improvement and can be seen as a lack of professional diligence in advocating for best practices. Professional reasoning. When faced with such a dilemma, a CES should follow a structured decision-making process. First, thoroughly understand all applicable regulations regarding waste generation, characterization, handling, and disposal. Second, assess the potential environmental and health risks associated with different waste management options. Third, evaluate the economic implications of each option, considering both short-term costs and long-term liabilities. Fourth, engage in open and transparent communication with management, presenting the regulatory requirements, potential risks, and the benefits of best practices, including waste minimization. Document all assessments, recommendations, and decisions. If management insists on a non-compliant or environmentally unsound approach, the CES must consider their ethical obligations and potentially escalate the issue or seek guidance from professional bodies. Question 10. The monitoring system demonstrates a consistent trend of exceeding the permitted discharge limits for a specific pollutant under the facility's National Pollutant Discharge Elimination System, NPDES, permit. The facility manager is concerned about potential fines and operational disruptions and has asked you to review the data and recommend a course of action, emphasizing the need to avoid immediate regulatory notification if possible. Option A. Continue to operate as normal and only report the exceedances if a formal inspection is conducted by the regulatory agency. Option B. Immediately report the exceedances to the relevant state environmental agency, initiate an investigation into the cause, and develop a plan for corrective actions to bring the discharge back into compliance with the NPDES permit. Option C. Cease all discharge operations immediately until the cause of the exceedances can be fully identified and rectified, without prior notification to the regulatory agency. Option D. Adjust the monitoring equipment calibration to bring the readings within the permitted limits before reporting any data to the regulatory agency. The correct answer is B. Immediately report the exceedances to the relevant state environmental agency, initiate an investigation into the cause, and develop a plan for corrective actions to bring the discharge back into compliance with the NPDES permit. Explanation. This scenario presents a professional challenge due to the conflict between immediate operational needs and long-term environmental compliance, particularly concerning potential exceedances of permitted discharge limits. The certified environmental scientist must exercise sound professional judgment, balancing the urgency of production with the legal and ethical obligations to protect environmental quality. The correct approach involves immediate, transparent reporting of the monitoring data to the relevant regulatory agency, coupled with a proactive investigation into the cause of the exceedance and the development of a corrective action plan. This aligns with the principles of the Clean Water Act (CWA), which mandates reporting of permit violations and requires facilities to operate within their authorized discharge parameters. Ethically, it upholds the professional responsibility to act with integrity and to prioritize environmental protection. This approach demonstrates best professional practice by adhering to regulatory requirements, fostering trust with the agency, and mitigating potential environmental harm. An incorrect approach would be to delay reporting or to attempt to manipulate the data to avoid flagging an exceedance. This directly violates the reporting requirements of the CWA and potentially other federal, state, or local environmental laws. Ethically, it constitutes a breach of trust and a failure to uphold professional integrity. Such actions could lead to significant penalties, including fines and legal action, and damage the reputation of both the individual and the organization. Another incorrect approach would be to cease operations immediately without proper investigation or consultation. While seemingly protective, this could lead to unnecessary economic disruption and may not be the most effective solution if the exceedance is minor or easily rectifiable. It bypasses the established regulatory process for addressing permit violations, which typically involves investigation and corrective action rather than an immediate shutdown. A third incorrect approach would be to only address the issue internally without notifying the regulatory agency. This fails to meet the explicit reporting obligations under environmental laws like the CWA. While internal investigation is a necessary step, it is insufficient on its own to satisfy legal and ethical responsibilities. The professional decision-making process for similar situations should involve 1. Immediate assessment of the data and its implications. 2. Consultation with internal stakeholders and legal counsel if necessary. 3. Prompt and accurate reporting to the regulatory authority. 4. Thorough investigation of the root cause. 5. Development and implementation of a corrective action plan. And 6. Ongoing monitoring to ensure compliance. This systematic approach ensures both legal compliance and ethical conduct. Question 11. During the evaluation of an environmental impact assessment IA for a proposed industrial facility, which approach best demonstrates adherence to best professional practice in assessing the adequacy of proposed mitigation measures? Option A. Conducting a thorough review of the scientific literature and expert opinion to determine the likely effectiveness of the proposed mitigation measures in reducing identified environmental impacts to acceptable levels and assessing the feasibility of their implementation. Option B. Relying primarily on the proponent's assurances and the inclusion of mitigation measures in the project plan to conclude that they are adequate, assuming regulatory approval implies their sufficiency. Option C. Focusing on the comprehensive identification of all potential environmental impacts and ensuring robust public consultation on these impacts, while giving less weight to the detailed evaluation of the proposed mitigation strategies. Option D. Verifying that the proposed mitigation measures are clearly described and that the proponent has committed to their implementation without independently assessing their scientific efficacy or feasibility. The correct answer is D. Verifying that the proposed mitigation measures are clearly described and that the proponent has committed to their implementation without independently assessing their scientific efficacy or feasibility. Explanation. The scenario presents a common challenge in environmental impact assessment, IA, where the effectiveness of proposed mitigation measures needs to be rigorously evaluated. This requires a deep understanding of the EIA process, not just as a procedural checklist, but as a dynamic tool for achieving environmental protection. The professional challenge lies in discerning between superficial compliance and genuine environmental stewardship, particularly when faced with potentially inadequate proposals. The correct approach represents best professional practice because it prioritizes a thorough, evidence-based assessment of mitigation effectiveness, directly aligning with the core objectives of EIA, as mandated by regulatory frameworks. This involves critically examining the scientific basis for proposed measures, considering their feasibility, and ensuring they are proportionate to the identified impacts. Regulatory frameworks, such as those governing EIA in the US e.g., NEPA, emphasize the need for all practicable means consistent with the present and future needs of the nation to protect and enhance the quality of the environment. This necessitates a proactive and critical stance on mitigation, rather than passive acceptance. Ethical considerations also demand that environmental professionals act with integrity and competence, ensuring that their assessments lead to meaningful environmental outcomes. An incorrect approach that relies solely on the proponent's assurances fails to meet regulatory requirements for independent and objective assessment. It represents a failure to exercise professional due diligence and can lead to significant environmental harm going unmitigated, violating the ethical duty to protect the environment. Another incorrect approach that focuses only on the initial identification of impacts without a robust evaluation of mitigation neglects a crucial phase of the EIA process. EIA is not merely about identifying problems, but about proposing and verifying solutions. This oversight can result in a flawed EIA document that does not adequately inform decision-making. Finally, an approach that prioritizes public participation over scientific rigor. While public input is vital, can lead to decisions based on incomplete or misinformed perspectives if not grounded in sound scientific analysis of mitigation effectiveness. While public engagement is a cornerstone of EIA, it must be informed by a technically sound assessment of potential impacts and proposed mitigation. The professional decision-making process for similar situations should involve a systematic review of the EIA documentation against regulatory requirements and best practices. This includes critically evaluating the baseline data, the impact prediction methodologies, the proposed mitigation measures, and the monitoring plans. Professionals must ask, are the proposed measures technically sound? Are they likely to achieve the stated environmental objectives? Is there sufficient evidence to support their effectiveness? Is the monitoring plan adequate to verify their success? This critical, evidence-based approach ensures that the EIA process fulfills its purpose of informing decision-making for sustainable development. Question 12. The performance metrics show that a site exhibits moderate levels of petroleum hydrocarbons and chlorinated solvents in the unsaturated zone, with a shallow water table. The site is located in a densely populated urban area with limited space for large-scale operations. Regulatory agencies have emphasized a preference for in-situ treatment methods where feasible to minimize disruption and off-site transport. Considering these factors, which soil remediation technology would likely be the most appropriate and compliant choice? Option A, land treatment. Option B, soil vapor extraction. Option C, bioremediation. Option D, excavation and off-site disposal. Correct answer is B, soil vapor extraction. Explanation. This scenario presents a common challenge in environmental consulting, selecting the most appropriate soil remediation technology when faced with diverse contaminant types and site-specific constraints. The professional challenge lies in balancing effectiveness, cost, regulatory compliance, and potential environmental impacts. Careful judgment is required to avoid selecting a technology that is either technically inadequate, overly expensive, or fails to meet the stringent requirements of environmental regulations. The correct approach represents best professional practice because it prioritizes a comprehensive understanding of the site conditions and contaminant characteristics to select a technology that is both effective and compliant. This involves a thorough site characterization, risk assessment, and consideration of all applicable regulations. For instance, if the contaminants are volatile organic compounds, VOC, and the soil is permeable, soil vapor extraction, SV, might be the most efficient and cost-effective method, aligning with regulatory goals for contaminant reduction. This approach demonstrates due diligence and a commitment to achieving the desired environmental outcome within the legal framework. An incorrect approach, such as recommending excavation without a thorough assessment of contaminant depth and spread, could lead to excessive disposal costs and potential off-site environmental impacts, failing to meet the least burdensome or most protective principles often embedded in environmental statutes. Recommending bioremediation for non-biodegradable contaminants would be a regulatory failure, as it would not achieve the cleanup objectives mandated by regulatory agencies. Similarly, proposing chemical oxidation for highly mobile contaminants without adequate containment could result in the spread of contaminants, violating regulations designed to prevent further environmental degradation. Phytoremediation, while promising, has limitations regarding contaminant types and uptake rates. Recommending it without verifying its suitability for the specific contaminants and site conditions would be an ethical failure, potentially leading to ineffective cleanup and prolonged site contamination. Professional decision-making in such situations requires a systematic process. 1. Thoroughly understand the site's hydrogeology, soil characteristics, and the nature and extent of contamination. 2. Review all applicable federal, state, and local environmental regulations and guidance documents relevant to the specific contaminants in site. 3. Evaluate the advantages and disadvantages of various remediation technologies in the context of the site-specific conditions and regulatory requirements. 4. Conduct a comparative analysis of feasible technologies, considering effectiveness, cost, timeline, potential risks, and long-term sustainability. 5. Select the technology that best meets the cleanup objectives, regulatory standards, and is technically sound and economically viable. 6. Document the decision-making process thoroughly, including the rationale for selecting the chosen technology and rejecting others, to demonstrate compliance and professional judgment. Question 13. Benchmark analysis indicates that a manufacturing facility operating under a National Pollutant Discharge Elimination System (NPDES) permit issued pursuant to the Clean Water Act (CWA needs a thorough evaluation of its wastewater discharge practices to ensure ongoing regulatory adherence. The facility has experienced some minor operational disruptions in the past year, raising concerns about potential compliance issues. Which audit approach would be most appropriate to comprehensively assess the facility's compliance with all relevant CWA requirements and its NPDES permit conditions? Option A, a management system audit. Option B, a preliminary site assessment. Option C, a comprehensive compliance audit. Option D, a focused audit on a single permit condition. The correct answer is C, a comprehensive compliance audit. Explanation: scenario analysis. This scenario presents a common challenge in environmental auditing, balancing the need for thorough compliance assessment with the practical constraints of time and resources. The environmental scientist must determine the most effective audit type to identify potential noncompliance with the Clean Water Act (CWA) regulation, specifically concerning wastewater discharge permits. The challenge lies in selecting an audit approach that is both comprehensive enough to uncover systemic issues and efficient enough to be feasible within the given parameters. Overlooking critical areas due to an inappropriate audit type can lead to significant regulatory penalties, environmental damage, and reputational harm. Correct approach analysis. A comprehensive compliance audit is the best professional practice in this scenario. This approach is designed to systematically evaluate an organization's adherence to all applicable environmental laws, regulations, and permit conditions. For the CWA, this would involve reviewing discharge monitoring reports, operational logs, sampling data, and facility infrastructure to ensure compliance with effluent limitations, monitoring requirements, and reporting obligations. This type of audit directly addresses the core objective of verifying compliance with specific regulatory frameworks, making it the most effective method for identifying potential violations and ensuring the facility operates within its permit. Incorrect approaches analysis. A preliminary site assessment, while useful for initial screening, is generally not sufficient for a thorough compliance audit. Its primary purpose is to identify potential environmental concerns or risks, not to systematically verify adherence to specific regulatory requirements like those mandated by the CWA. Relying solely on this would likely miss detailed compliance gaps. A management system audit, while valuable for assessing the effectiveness of environmental management systems (EMS), focuses on the processes and procedures in place rather than the direct outcome of compliance with specific regulations. An EMS might be well documented, but the actual operations could still be non-compliant with CWA permit conditions. This audit type is more about the how of environmental management, not the if of regulatory adherence. A focused audit on a single permit condition, while efficient, is insufficient when the objective is to assess overall compliance with the CWA. The CWA encompasses numerous requirements beyond a single permit condition, including record-keeping, reporting, and potential spill prevention measures. Limiting the audit scope in this manner risks overlooking other significant areas of noncompliance. Professional reasoning. When faced with a compliance assessment objective, environmental scientists should first identify the primary regulatory framework governing the facility's operations. Then, they should select an audit type that is specifically designed to evaluate adherence to that framework. A comprehensive compliance audit is the most robust method for this purpose. If resources are limited, a risk-based approach can be employed to prioritize areas within a comprehensive audit, but the overall objective should remain broad compliance verification. Always ensure audit protocols are aligned with the specific regulatory requirements being assessed, and that findings are documented meticulously for corrective action planning and reporting. Question 14. Regulatory review indicates a need to update local land use policies to better incorporate smart growth principles and enhance environmental protection. The Planning Department is considering several approaches to guide future development, including revising zoning ordinances, exploring new policy instruments, and integrating environmental impact assessments more effectively into the planning process. As a certified environmental scientist, You are asked to advise on the most effective strategy for developing these updated policies, considering the interplay between policy development, land use planning, and zoning regulations. Which of the following approaches best aligns with best professional practice for this situation? Option A. Suggest the implementation of a new set of environmental regulations that are separate from land use planning and zoning to avoid complexity in the policy development process. Option B. Advocate for the adoption of policies primarily driven by developer input to expedite the development process, focusing on economic growth over detailed environmental and planning considerations. Option C. Recommend a comprehensive review of existing zoning regulations and the introduction of performance-based zoning, coupled with an assessment of transferable development rights as policy instruments, ensuring alignment with smart growth principles and environmental impact mitigation strategies. Option D. Propose immediate amendments to existing zoning ordinances to restrict development in environmentally sensitive areas, without a broader analysis of policy instruments or smart growth integration. Correct answer is C. Recommend a comprehensive review of existing zoning regulations and the introduction of performance-based zoning, coupled with an assessment of transferable development rights as policy instruments, ensuring alignment with smart growth principles and environmental impact mitigation strategies. Explanation. Scenario analysis. This scenario presents a common challenge in environmental planning, balancing competing interests and scientific data within a complex policy development process. The professional is tasked with advising on a new land use policy that aims to integrate smart growth principles while addressing existing zoning regulations and potential environmental impacts. The challenge lies in synthesizing diverse stakeholder input, scientific findings, and the nuances of policy instruments to recommend a course of action that is both environmentally sound and practically implementable within the existing legal and planning framework. The pressure to deliver a robust recommendation that can withstand scrutiny from regulators, developers, and community groups necessitates a thorough and defensible decision-making process. Correct approach analysis. The correct approach involves a systematic evaluation of policy instruments and their alignment with smart growth principles and existing land use planning tools. This includes assessing how different instruments, such as transferable development rights or performance zoning, can incentivize desired development patterns while mitigating environmental concerns. It requires understanding the interplay between policy development, land use planning, and zoning regulations, ensuring that proposed changes are legally feasible and contribute to sustainable outcomes. This approach represents best professional practice because it is grounded in a comprehensive understanding of environmental policy and planning theory, adhering to the principles of evidence-based decision-making and regulatory compliance. It prioritizes a holistic view, considering the long-term implications of policy choices and their impact on environmental quality and community well-being, aligning with the ethical obligations of a certified environmental scientist to protect public health and the environment. Incorrect approaches analysis. One incorrect approach would be to solely focus on implementing new zoning regulations without considering their compatibility with broader smart growth principles or the effectiveness of various policy instruments. This fails to acknowledge the integrated nature of environmental policy and planning, potentially leading to fragmented or ineffective outcomes. It represents a regulatory failure by not fully leveraging the available policy tools and a planning failure by not adopting a comprehensive, forward-looking strategy. Another incorrect approach would be to prioritize stakeholder demands without rigorous scientific or regulatory analysis. While stakeholder engagement is crucial, decisions must be informed by environmental science and legal frameworks. Ignoring these aspects can lead to policies that are not environmentally protective, legally sound, or sustainable in the long term, constituting an ethical failure to uphold professional responsibilities. A third incorrect approach would be to recommend policy instruments that are not legally permissible or are incompatible with existing land use planning frameworks. This demonstrates a lack of due diligence in understanding the regulatory landscape and the practical constraints of implementation, leading to wasted resources and potentially undermining the policy development process. This is a significant regulatory and professional failure. Professional reasoning. Professionals should employ a structured decision-making framework that begins with a thorough understanding of the problem and the relevant regulatory environment. This involves 1. Defining the objectives. Clearly articulate the goals of the policy, including environmental protection, smart growth integration, and community needs. 2. Information gathering. Collect and analyze relevant scientific data, existing regulations, and stakeholder input. 3. Policy instrument evaluation. Assess the suitability, effectiveness, and legal feasibility of various policy instruments in achieving the defined objectives. 4. Impact assessment. Evaluate the potential environmental, social, and economic impacts of proposed policy changes. 5. Recommendation development. Formulate a clear, defensible recommendation based on the analysis, ensuring alignment with regulatory requirements and best practices. 6. Communication and justification. Clearly communicate the rationale behind the recommendation to stakeholders and decision makers. Question 15. The evaluation methodology shows a proposed industrial development project that has the potential for significant environmental impacts. A key consideration in the project's approval process is how to best incorporate the diverse perspectives and concerns of all potentially affected parties. Which of the following approaches best reflects ethical and regulatory best practices for environmental decision-making in this scenario? Option A. Focus engagement efforts on the primary industry stakeholders and investors, as their financial interests are most directly tied to the project's success, and address community concerns only if they pose a significant risk to project timelines. Option B. Prioritize the economic benefits of the project and proceed with development after ensuring all minimum regulatory requirements for environmental protection are met, dismissing environmental concerns as secondary to job creation. Option C. Conduct a series of public information sessions to present the project's environmental impact assessment findings and allow for limited question and answer periods, focusing primarily on addressing concerns raised by regulatory agencies. Option D. Implement a comprehensive stakeholder engagement strategy that actively seeks input from local communities, indigenous groups, environmental organizations, and regulatory bodies throughout the project lifecycle, ensuring their concerns inform project design and mitigation measures. The correct answer is C. Conduct a series of public information sessions to present the project's environmental impact assessment findings and allow for limited question and answer periods, focusing primarily on addressing concerns raised by regulatory agencies. Explanation. The evaluation methodology shows a proposed industrial development project that has the potential for significant environmental impacts. The challenge lies in balancing economic development with environmental protection and ensuring that all affected stakeholders are considered and their concerns addressed equitably. This scenario is professionally challenging because it requires navigating complex ethical considerations, including environmental justice, the principles of sustainable development, and the responsibilities of corporate social responsibility, all within the framework of relevant environmental regulations. Careful judgment is required to ensure that the decision-making process is transparent, inclusive, and leads to outcomes that are environmentally sound and socially responsible. The correct approach represents best professional practice because it prioritizes a comprehensive stakeholder engagement process that actively seeks input from all potentially affected parties, including local communities, indigenous groups, environmental organizations, and regulatory bodies. This aligns with the principles of environmental justice, which demand that no group bears a disproportionate share of negative environmental consequences resulting from industrial, governmental, and commercial operations or policies. Furthermore, it embodies the core tenets of sustainable development by seeking to integrate environmental, social, and economic considerations into the decision-making process, ensuring long-term viability. Active stakeholder engagement is also a key component of effective corporate social responsibility, demonstrating a commitment to operating ethically and contributing positively to society. An incorrect approach that fails to adequately consult with or consider the concerns of a vulnerable community living downstream from the proposed development represents a significant ethical and regulatory failure. This failure violates the principles of environmental justice by potentially exposing this community to disproportionate environmental harm without their informed consent or meaningful participation. It also undermines the principles of sustainable development by neglecting the social equity dimension. From a regulatory perspective, depending on the specific jurisdiction's environmental impact assessment (IA) requirements, such a failure could lead to legal challenges, project delays, and reputational damage. Another incorrect approach that solely focuses on meeting minimum regulatory compliance without proactively seeking broader stakeholder input or considering potential cumulative impacts demonstrates a narrow and potentially unethical interpretation of professional responsibility. While meeting regulations is essential, it does not fulfill the broader ethical obligations of environmental stewardship and corporate social responsibility. This approach risks overlooking critical environmental and social issues that may not be explicitly covered by current regulations, but are nonetheless important for long-term sustainability and community well-being. A third incorrect approach that prioritizes the economic benefits of the project above all else, dismissing environmental concerns as secondary, is ethically unsound and contrary to the principles of sustainable development. This approach neglects the intrinsic value of the environment and the long-term consequences of ecological degradation. It also fails to uphold corporate social responsibility by prioritizing profit over the well-being of the environment and affected communities. Such a stance can lead to irreversible environmental damage and significant social conflict. A professional decision-making process for similar situations should involve a systematic and iterative approach. This begins with a thorough understanding of the project's potential environmental and social impacts. It then requires identifying all relevant stakeholders, assessing their interests and potential impacts, and developing a robust engagement plan. This plan should facilitate meaningful two-way communication, allowing for the incorporation of stakeholder feedback into project design and mitigation strategies. Professionals must also continuously evaluate the project against the principles of environmental justice and sustainable development, ensuring that decisions are not only legally compliant, but also ethically defensible and contribute to long-term environmental and social well-being. Question 16. Process analysis reveals that a certified environmental scientist is tasked with evaluating the air quality impact of a new industrial facility in a region with existing air quality concerns. The scientist must determine the facility's contribution to ambient air pollution and ensure compliance with relevant air quality regulations. Which of the following monitoring and assessment strategies would best fulfill these objectives and adhere to regulatory frameworks? Option A. Conduct ambient air quality monitoring at a single location downwind of the facility, assuming this single point adequately represents regional air quality. Option B. Conduct continuous ambient air quality monitoring at multiple locations around the facility and implement source-specific emission monitoring for key pollutants directly from the facility stacks. Option C. Implement a comprehensive source-specific emission monitoring program for all potential pollutants from the facilities stacks without any ambient air quality monitoring. Option D. Focus exclusively on indoor air quality monitoring within nearby residential areas to assess potential health impacts. The correct answer is B. Conduct continuous ambient air quality monitoring at multiple locations around the facility and implement source-specific emission monitoring for key pollutants directly from the facility stacks. Explanation. Scenario analysis. This scenario presents a common challenge in environmental consulting, where multiple monitoring strategies can be employed, each with its own strengths and weaknesses. The professional challenge lies in selecting the most appropriate and defensible approach for assessing compliance with ambient air quality standards, considering the specific context of industrial emissions and potential public health impacts. This requires a deep understanding of regulatory requirements, monitoring methodologies, and the principles of data interpretation. Correct approach analysis. The correct approach involves a comprehensive strategy that combines both ambient air quality monitoring and source-specific emission monitoring. Ambient monitoring provides a direct measure of the air quality experienced by the public and is essential for determining compliance with established national ambient air quality standards, NOx. Source monitoring, on the other hand, is crucial for identifying and quantifying emissions from specific industrial facilities, which is often a regulatory requirement for permitting and control strategy development. Integrating data from both types of monitoring allows for a robust assessment of the contribution of industrial sources to ambient air quality, facilitating effective regulatory enforcement and pollution control. This integrated approach aligns with the principles of the Clean Air Act, which mandates both ambient standards and controls on emissions from stationary sources. Incorrect approach is analysis. An approach solely focused on ambient air quality monitoring, without considering source emissions, is insufficient because it may not identify the specific contributors to any exceedances of standards. This failure to pinpoint sources hinders effective regulatory action and the implementation of targeted control measures, potentially violating the spirit and letter of regulations that require source accountability. An approach exclusively focused on source emission monitoring, without concurrent ambient monitoring, is also inadequate. While it quantifies emissions, it does not directly assess the impact of those emissions on the surrounding environment and public health. This neglects the primary objective of ambient air quality standards, which is to protect human health and welfare, and fails to provide the necessary data for demonstrating compliance with NOx. An approach that relies solely on indoor air quality monitoring is inappropriate for assessing ambient air quality standards. Indoor air quality is influenced by a multitude of factors, including building materials, occupant activities, and ventilation, and is distinct from the broader atmospheric conditions addressed by ambient standards. Focusing on indoor air quality would fail to meet the regulatory requirements for assessing outdoor air pollution and its impact on the general population. Professional reasoning. Professionals must first identify the specific regulatory objectives. In this case, the primary objective is to assess compliance with ambient air quality standards, which necessitates ambient monitoring. However, given the presence of industrial sources, understanding their contribution is also critical for effective pollution control and regulatory compliance. Therefore, a dual approach of ambient and source monitoring is the most defensible and professionally sound. This involves selecting appropriate monitoring methods based on the pollutants of concern and the regulatory requirements, e.g., EPA reference methods for NOx, ensuring data quality through rigorous QA/QC protocols, and interpreting the data in the context of established standards and emission limits. Question 17. Implementation of a comprehensive environmental sampling program for a Superfund site risk assessment requires careful consideration of multiple factors. Which of the following approaches best ensures the collection of legally defensible and scientifically sound data for characterizing potential risks? Option A. Utilizing uncalibrated field instruments for real-time measurements to reduce costs and proceeding with sample collection based on initial, potentially inaccurate readings. Option B. Developing a detailed sampling and analysis plan (SAP) that specifies sampling location, methods, preservation techniques, and robust QA/QC procedures, including field blanks, duplicate samples, and the use of calibrated field instrumentation. Option C. Collecting samples rapidly from a few strategically chosen locations without extensive QA/QC measures to expedite the initial site characterization. Option D. Relying solely on grab samples for all media, assuming contaminant concentrations are static and omitting field blanks to save time. The correct answer is B. Developing a detailed sampling and analysis plan (SAP) that specifies sampling locations, methods, preservation techniques, and robust QA/QC procedures, including field blanks, duplicate samples, and the use of calibrated field instrumentation. Explanation. This scenario presents a professional challenge due to the inherent uncertainties in environmental sampling and the critical need to ensure data defensibility for risk assessment. The certified environmental scientist must balance the practicalities of field operations with stringent regulatory requirements for data quality. The goal is to collect representative samples that accurately reflect site conditions, enabling a reliable assessment of potential environmental risks to human health and ecosystems. Failure to adhere to proper sampling design, collection, preservation, and QA/QC protocols can lead to biased data, inaccurate risk assessments, and potentially costly remediation decisions or regulatory noncompliance. The correct approach represents best professional practice because it systematically addresses all critical components of environmental sampling for risk assessment. A well-defined sampling design ensures that samples are collected from locations and depths representative of potential contaminant sources and pathways, directly supporting the risk assessment objectives. Appropriate sample collection methods minimize cross-contamination and ensure sample integrity. Proper sample preservation maintains the chemical and physical characteristics of the sample from collection to laboratory analysis, preventing degradation or alteration. Robust QA/QC procedures, including field blanks, duplicate samples, and performance audits, provide objective evidence of data reliability and are mandated by regulatory frameworks to ensure that the data is scientifically sound and legally defensible. The use of calibrated field instrumentation ensures accurate real-time measurements, which are often crucial for guiding sampling efforts and initial site characterization. Adherence to these principles is fundamental to meeting the requirements of environmental regulations and ethical professional conduct. An incorrect approach that prioritizes speed over thoroughness by skipping field blanks and duplicates samples is professionally unacceptable. This failure directly violates QA/QC requirements, which are essential for demonstrating data integrity. Without these checks, there is no objective way to assess potential field contamination or laboratory variability, rendering the data unreliable for risk assessment and potentially leading to erroneous conclusions about environmental conditions. Another incorrect approach that involves using uncalibrated field instrumentation is also professionally unacceptable. Environmental regulations and best practices mandate the use of calibrated equipment to ensure the accuracy of measurements. Uncalibrated instruments can produce significantly biased readings, compromising the validity of any data collected and the subsequent risk assessment. This represents a failure in due diligence and a disregard for data quality standards. A third incorrect approach that relies solely on grab samples without considering the temporal variability of contaminants, especially in dynamic environments like surface water or air, is professionally unsound. While grab samples are a valid technique, their suitability depends on the sampling design and the nature of the contaminant. For risk assessment, understanding the range of contaminant concentrations over time is often crucial. Failing to account for this variability can lead to an underestimation or overestimation of exposure, thereby undermining the accuracy of the risk assessment. This demonstrates a lack of understanding of sampling design principles in relation to risk assessment objectives. The professional reasoning process for similar situations should involve a thorough understanding of the risk assessment objectives, the specific contaminants of concern, the environmental media to be sampled, and the relevant regulatory requirements. This understanding informs the development of a comprehensive sampling and QA/QC plan. Professionals must critically evaluate each step of the sampling process, from design to data analysis, ensuring that it aligns with these objectives and requirements. Continuous vigilance regarding data quality and adherence to established protocols are paramount for producing defensible and reliable environmental data. Question 18. Operational review demonstrates an undocumented discharge of a chemical substance into a nearby waterway from a facility's secondary containment area, which appears to have been compromised by recent extreme weather. The discharge is not immediately visible at the point of entry into the waterway due to dense vegetation. Which of the following represents the most appropriate initial course of action for the certified environmental scientist? Option A. Dispatch a team to the site to immediately contain the discharge at its source, conduct preliminary visual assessments and sample collection for immediate analysis, and prepare for prompt notification to the relevant environmental regulatory authority. Option B. Advise facility management to temporarily cease all operations that could contribute to further discharge, and await further instructions from the environmental regulatory authority before taking any investigative action. Option C. Immediately initiate a comprehensive remediation plan for the waterway, focusing on the most likely chemical constituents based on facility inventory, and defer reporting to regulatory agencies until the remediation is complete. Option D. Document the visual evidence of the compromised containment and the potential discharge, and recommend that facility management monitor the waterway for any visible signs of impact over the next 48 hours before considering further action. The correct answer is C. Immediately initiate a comprehensive remediation plan for the waterway, focusing on the most likely chemical constituents based on facility inventory, and defer reporting to regulatory agencies until the remediation is complete. Explanation. Scenario analysis. This scenario presents a common challenge for certified environmental scientists, balancing regulatory compliance with operational efficiency and potential environmental risks. The discovery of a previously undocumented discharge requires immediate attention, but the urgency must be tempered with a systematic and legally sound approach. The challenge lies in determining the appropriate response given incomplete information and the potential for significant environmental and legal repercussions. A hasty or misinformed decision could lead to non-compliance, environmental damage, and reputational harm. Correct approach analysis. The correct approach involves a multi-step process that prioritizes immediate containment and assessment, followed by thorough investigation and regulatory notification. This aligns with the principles of environmental stewardship and the legal obligations under relevant environmental statutes, e.g., Clean Water Act in the U.S., or equivalent national legislation. The initial step of containing the discharge is crucial to prevent further environmental degradation. Subsequently, conducting a detailed site assessment and sample analysis provides the necessary data to understand the nature and extent of the contamination. Finally, timely and accurate reporting to the relevant regulatory agencies is a mandatory legal requirement, demonstrating transparency and facilitating a coordinated response. This methodical approach ensures that all aspects of the problem are addressed in a responsible and legally compliant manner, minimizing both environmental impact and legal liability. Incorrect approaches analysis. One incorrect approach involves delaying notification to regulatory agencies while attempting to resolve the issue internally. This is a significant regulatory failure as it violates mandatory reporting requirements. Environmental laws typically mandate prompt reporting of spills or discharges, and failure to do so can result in severe penalties, including fines and legal action. Furthermore, attempting to resolve the issue without regulatory oversight can lead to inadequate remediation efforts, potentially exacerbating environmental damage. Another incorrect approach is to immediately initiate extensive remediation without a proper assessment and regulatory consultation. While proactive, this can be inefficient and may not address the root cause of the discharge. It also bypasses the regulatory process, which often requires agency approval for remediation plans. This can lead to wasted resources, ineffective solutions, and potential noncompliance if the chosen remediation strategy is not acceptable to the authorities. A third incorrect approach is to dismiss the discharge as minor without sufficient data. Environmental impacts can be cumulative and subtle. Underestimating the significance of a discharge, even if it appears small, can lead to long-term environmental harm and regulatory scrutiny if discovered later. This demonstrates a failure in due diligence and a lack of adherence to the precautionary principle, which is often embedded in environmental regulations. Professional reasoning. Certified environmental scientists must employ a structured decision-making framework when faced with environmental incidents. This framework typically involves 1. Immediate response and containment to prevent further harm. 2. Thorough assessment and data collection to understand the problem. 3. Consultation with relevant stakeholders, including regulatory bodies. 4. Development and implementation of appropriate corrective actions and remediation plans, often in collaboration with regulators. 5. Documentation and reporting throughout the process. This systematic approach ensures that decisions are informed, legally compliant, ethically sound, and environmentally responsible. Question 19. The control framework reveals that a certified environmental scientist has identified elevated levels of a known carcinogen in groundwater beneath a residential area. Preliminary toxicological data suggests a plausible link between chronic low-level exposure via drinking water and an increased incidence of a specific cancer in the local population. The scientist is under pressure from a developer, who is funding the assessment, to present the findings in a manner that minimizes public concern and avoids costly remediation efforts. What is the most ethically and professionally sound approach for the certified environmental scientist to take? Option A. Emphasize the limitations of current toxicological data and the inherent uncertainties in risk assessment to argue that no definitive conclusions can be drawn about potential health effects, thus deferring any action or reporting of significant risk. Option B. Omit detailed discussion of specific exposure pathways that are scientifically plausible but might be perceived as alarming, and use vague language regarding dose-response relationships to avoid creating undue public anxiety. Option C. Present a comprehensive report detailing the toxicological principles, identified exposure pathways, dose-response relationships, potential health effects, and a thorough risk assessment, clearly articulating the uncertainties but not downplaying the potential for adverse health outcomes, and ensuring all findings are communicated to relevant regulatory agencies and stakeholders. Option D. Focus the report on the most conservative worst-case exposure scenarios, which are highly improbable, to demonstrate that even under extreme conditions, the risk is manageable, thereby reassuring the public and the developer. The correct answer is C. Present a comprehensive report detailing the toxicological principles, identified exposure pathways, dose-response relationships, potential health effects, and a thorough risk assessment, clearly articulating the uncertainties but not downplaying the potential for adverse health outcomes, and ensuring all findings are communicated to relevant regulatory agencies and stakeholders. Explanation: this scenario presents a significant ethical and professional challenge for a certified environmental scientist, CES, operating under U.S. regulatory frameworks, specifically those governed by the EPA and related state environmental agencies. The core challenge lies in balancing the scientific imperative to accurately report potential health risks with the pressure to downplay findings that could lead to costly remediation or public outcry. The CES must navigate the complexities of toxicological principles, exposure pathways, dose-response relationships, and the inherent uncertainties in risk assessment, all while adhering to professional ethics and regulatory mandates. The correct approach emphasizes transparency, scientific integrity, and adherence to established risk assessment methodologies. This involves clearly communicating the potential health effects of the identified contaminants, detailing the likely exposure pathways for the local population, and presenting the dose-response information in an understandable manner. Crucially, it requires a robust risk assessment that acknowledges uncertainties, but does not shy away from presenting the most scientifically defensible conclusions regarding potential health impacts. This aligns with the ethical obligations of a CES to protect public health and the environment, as mandated by regulations like the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, and the Toxic Substances Control Act, TSCA, which require accurate reporting and risk characterization. Best professional practice dictates that the CES should provide all relevant information to decision makers, allowing them to make informed choices, even if those choices are difficult. An incorrect approach would be to selectively present data or to use overly cautious language that obscures the potential severity of the health risks. For instance, focusing solely on low probability, high-dose scenarios while ignoring more probable, lower-dose exposures that could still lead to adverse health effects would be a failure to adequately characterize risk. Another incorrect approach would be to omit or minimize discussion of specific exposure pathways that are scientifically plausible, thereby underestimating the potential for human contact with the contaminants. Ethically, this constitutes a breach of professional duty, as it misleads stakeholders and potentially endangers public health. Regulatory failures would include non-compliance with reporting requirements under CERCLA or TSCA, which mandate comprehensive risk assessments and communication of findings. Furthermore, such actions could violate professional codes of conduct for environmental scientists, which prioritize public welfare. The professional decision-making process for similar situations should involve a systematic review of the scientific data, a thorough application of established risk assessment protocols, and a commitment to clear, unbiased communication. The CES should consult relevant EPA guidance documents and state-specific regulations for risk assessment and public notification. If faced with pressure to alter findings, the CES should document all communications and concerns, and if necessary, seek guidance from professional organizations or legal counsel. The ultimate goal is to ensure that decisions are based on sound science and a complete understanding of potential environmental and health risks. Question 20. Cost-benefit analysis shows that an industrial expansion project offers significant economic returns, but it requires the development of a portion of a high biodiversity wetland. Which approach best balances the economic benefits with the ecological integrity of the wetland ecosystem? Option A. Conduct a comprehensive assessment of the wetland's ecosystem services, including water purification, flood control, and habitat provision, and compare their quantified or semi-quantified value against the projected economic benefits of the industrial expansion, while also evaluating the potential impacts on ecological succession and resilience. Option B. Prioritize the immediate economic gains from the industrial expansion, assuming that any ecological impacts can be mitigated through minor landscaping and replanting efforts after construction. Option C. Perform a general qualitative assessment of the wetland's ecological importance, noting its aesthetic value and general biodiversity, without attempting to quantify specific ecosystem services or their economic equivalents. Option D. Focus exclusively on protecting a single, rare bird species known to inhabit the wetland, as its conservation is often a high-profile requirement, and assume that protecting this species will indirectly safeguard the rest of the ecosystem. Correct answer is A. Conduct a comprehensive assessment of the wetland's ecosystem services, including water purification, flood control, and habitat provision, and compare their quantified or semi-quantified value against the projected economic benefits of the industrial expansion, while also evaluating the potential impacts on ecological succession and resilience. Explanation: scenario analysis. This scenario presents a common challenge for certified environmental scientists, balancing economic development with ecological preservation. The proposed industrial expansion directly impacts a sensitive wetland ecosystem, raising questions about the long-term viability of ecosystem services versus short-term economic gains. The professional challenge lies in objectively evaluating the ecological significance of the wetland, quantifying its services, and comparing these to the projected economic benefits, all while adhering to stringent environmental regulations. This requires a deep understanding of ecosystem dynamics, biodiversity, and the principles of ecological succession, as well as the ability to translate ecological values into a framework that can be understood and utilized in decision-making processes. Correct approach analysis. The correct approach emphasizes a comprehensive assessment of the wetland's ecosystem services, considering both tangible and intangible benefits. This aligns with the principles of ecological economics and is often mandated by environmental impact assessment (IA) regulations, such as those under the U.S. National Environmental Policy Act (NEPA) or similar state-level equivalents. A thorough evaluation of biotic and abiotic components, energy flow, nutrient cycling, trophic levels, and biodiversity is crucial for understanding the wetland's functional integrity and its capacity to provide services like water purification, flood control, and habitat provision. The analysis should also consider the potential impacts of the industrial expansion on ecological succession and ecosystem resilience, predicting how these changes might affect the long-term provision of services. This approach represents best professional practice because it is scientifically rigorous, ethically responsible, and legally compliant, ensuring that decisions are informed by a holistic understanding of environmental impacts and the value of natural capital. It prioritizes the precautionary principle and the sustainability of natural resources. Incorrect approach is analysis, focusing solely on immediate economic gains without a thorough ecological assessment, is a significant regulatory and ethical failure. This approach disregards the mandates of environmental protection laws that require consideration of ecological impacts. It represents a failure to uphold professional ethics by prioritizing short-term financial interests over the long-term health of the environment and the public good derived from ecosystem services. Prioritizing the preservation of a single charismatic species without considering the broader ecosystem functions and services it represents is also problematic. While species protection is important, an ecosystem-level approach is often required by regulations to ensure the overall health and stability of the environment. This narrow focus can lead to suboptimal resource allocation and may not adequately address the complex interdependencies within the ecosystem, potentially failing to protect other critical functions or species. Adopting a purely qualitative assessment of ecological impacts without attempting to quantify or at least systematically evaluate the ecosystem services provided is insufficient. Many environmental regulations require a more robust analysis, often involving quantitative or semi-quantitative methods to demonstrate the significance of impacts and the value of mitigation measures. A purely qualitative approach risks underestimating the true value of the ecosystem and its services, leading to decisions that are not adequately informed and potentially violate the spirit, if not the letter, of environmental laws. Professional reasoning. Certified environmental scientists must employ a systematic science-based decision-making process. This involves 1. Clearly defining the scope of the environmental assessment, including the specific ecosystem and the proposed project. 2. Conducting a thorough baseline study of the ecosystem's structure, function, and dynamics, including biotic and abiotic components energy flow, nutrient cycling, trophic levels, food webs, biodiversity, and current ecosystem services. 3. Evaluating the potential impacts of the proposed project on these ecological attributes and services, considering both direct and indirect effects, and short-term versus long-term consequences. 4. Quantifying or semi-quantifying the value of ecosystem services at risk and comparing this to the projected economic benefits of the project, using appropriate methodologies. 5. Identifying and evaluating potential mitigation and enhancement measures. 6. Recommending a course of action that is environmentally sound, economically justifiable, and legally compliant, adhering to the principles of sustainability and the precautionary principle. This structured approach ensures that all relevant factors are considered, leading to informed and defensible recommendations.